In this video, we will look into a relatively interesting problem that involves a, a block that is held by a string, okay, that's anchored to the wall, but this block slides along the inclined plane, and the inclined plane is free to move on a frictionless surface. So the block containing the inclined plane has mass capital M, and the little block has mass of little m. Okay. So the ask here, the question is, what is the acceleration of the block with mass little m? Okay. So that's what we need to figure out. So let's look at the free body diagram, okay, for the little block, okay, of mass little m. So if you see here, uh, the tension is pulling it upwards, okay. There's a normal force acting on, that's normal to the surface of the inclined plane. The weight acts vertically downwards, okay, and the components of the weight perpendicular to the inclined plane and parallel to the inclined plane are mg cosine theta and mg sine theta respectively. Okay, so if you look at the the free body diagram on the inclined plane block, okay, you will see that there is a tension, okay, that's pulling it towards the right. Now, so there is here the back tension of the rope here, okay, is t cosine theta, and it's pulling it back, okay, it's pulling it back. uh, so if, because this is t, the component of t in the horizontal direction is t cosine theta, right? And now the normal force exerted by the little block on the inclined plane is acting perpendicular to the surface of the inclined plane. Okay, so the component of n along the direction of motion of the inclined plane is n times sine of theta. Okay, so now the interesting thing here is this, that so the amount of rope consumed in moving this block down, okay, is the amount of rope that's consumed here. Okay, so whatever length here of the rope is extended, that same length of the rope, okay, disappears here. Okay, so therefore, and the if you denote the distance by which the little block has slid by Lm, okay, and the distance by which the big block has slid by L capital M, okay. So L capital M refers to the shortening of this particular segment of the string or the rope. Okay, so as this segment becomes shorter, okay, the inclined plane here moves towards the right. Okay, so because the length of the string never changes, okay, therefore any change, okay, any change in the length here, okay, any change in the length here is equal to the change in length there. Okay, and the change in length is what we are calling as L little m and L capital M. Okay, so now uh, so this represents the corresponding velocities of the block, of the little block and the big block. Okay, and if I put a double dot here, okay, that represents the acceleration of the little block. I'll write it this acceleration of the little block equals acceleration of the inclined plane. Okay, but bear in mind that these are in two different directions completely. Okay, so the little block is accelerating downwards like this, and the big block is accelerating towards the right. Okay, so if you look at the vectorial representation of the accelerations, okay, that's what this looks like. So we denote the relative sliding of the block, okay, the little block over the inclined plane, okay, as being in this direction, and the relative acceleration is denoted by a sub r. Okay, now the acceleration of the inclined plane is a sub m. So the net acceleration here is the sum of these two. Okay, so what we do here is we want to add this up vectorially. So we put a sub capital M going in this direction and a sub little r going in that direction. So therefore this is the resultant acceleration. But however, we are interested in the coordinate system that is fixed to the ground. Okay, that's the important part. The coordinate system is fixed to the ground, but the x here points downwards and the y points perpendicular to the inclined plane. So the x is along the inclined plane and y is perpendicular to the inclined plane. So if you see here, the component of acceleration that's parallel to the inclined plane, okay, equal to, so this is AR, the magnitude of AR, okay, minus magnitude of A sub capital M times cosine of theta. Okay, basically because this component resolved here, okay, essentially in order to do that, you take the acceleration a sub m and multiply by cosine of theta. Okay, so now we know that because of this constraint here, these two accelerations are equal. Okay, so what we do here is that, and that is equal to a, so we just get a times 1 minus cosine of theta. Okay, now the component of acceleration that is perpendicular to the inclined plane, okay, is nothing but this particular component, that is am times sine of theta. Now there is no corresponding component of a sub r because that is along the inclined plane, and there is no component of that acts in a perpendicular direction. Okay, so this is nothing but a times sine of theta. Okay, so now once we have this, it becomes relatively simple. Okay, so now if we do if you write the equation of motion for the little block along the inclined plane, okay, if we do then write the Newton's law, we get mg sine theta okay minus t equals m times a times 1 minus cosine theta. Okay, so that, because that's the acceleration that is parallel to the inclined plane. Okay, now if we write the same equation of motion for a direction perpendicular to the inclined plane, okay, so we get mg cosine theta we get mg cosine theta minus n equal to m times a times sine theta. Okay, so essentially what we are doing here is we are taking mg cosine theta, subtracting n from there. Okay, and that is the net force along the y direction, and the acceleration in the y direction is a sine theta. Okay, so therefore the force in the y direction is m times a times sine theta. Okay, so we have that part. Now if we want to do uh, the write the force equation for the inclined plane here, so we have the force acting towards the right, okay, is t, okay, and the force acting towards the left is t cosine theta, okay, and we add an n sine theta that's going towards the right, and that equals to m times a, and where a is the acceleration of the inclined plane, okay, and that is equal to a sub m. So this thing is equal to that, okay, and a sub m is equal to a, okay, so because of the constant equation that we have set up. Okay, so these are the three equations that need to be solved, right? So we have, so if you rewrite this equation at the bottom, so we will get, so I'm just going to overwrite this, okay, t times 1 minus cosine theta, okay, plus, so what we do here is that uh, so actually there's an error here, so we take that and replace this by capital M, because this is the Newton's law uh, for the inclined plane. So now we multiply the first equation by 1 minus cosine theta and the second equation by sine theta, and we add them together. So we have mg sine theta times 1 minus cosine theta, okay, uh, minus t times 1 minus cosine theta, okay, and to that we add the bottom equation multiplied by sine theta, mg cosine theta sine theta minus n sine theta. So this is equal to m times a times 1 minus cosine theta square equals, this is m times a times sine square theta, and we add these two together. So what happens here is that if we can see, so pretty much this term and that term, they cancel out, right? So we get mg sine theta. Now we understand that the sum of these two terms equal to m times a, right? So we can write as this as minus m times little a equals m times little m times a times 1 minus cosine theta square plus sine square theta. Okay, and so this reduces to 1 minus cosine 1 plus cosine square theta minus 2 cosine theta, okay, plus sine square theta. Okay, this is 2 times 1 minus cosine theta. Okay, so we can write this as m times a times or 2 times m times a times 1 minus cosine theta. Okay, and so therefore we rearrange the terms, we get mg sine theta equals a times capital M plus 2 times little m 1 minus cosine theta. Okay, and therefore here a equals mg sine theta divided by capital M plus 2 times little m 1 minus cosine theta. Okay, so that is the solution to this problem. Okay, so we had to make some interesting assumptions. Okay, so there are some assumptions here. The assumption is that there's absolutely no friction here. Okay, So, so, so that is number one. Number two is that this string doesn't extend. Okay, so it doesn't stretch. Therefore, any change in the length here is reflected there. Okay, and vice versa. So from that we got this constant equation. Okay, which means that the acceleration of the little block going downwards is equal to the acceleration of the big block moving sideways. Okay, and so what we did was that we resolved the accelerations, okay, along the inclined plane and perpendicular to the inclined plane. So we did that. So once we got that, okay, so the Newton's laws are pretty simple to write, right? So we wrote the Newton's laws for motion along the inclined plane and motion perpendicular to the inclined plane. Okay, and now this is the Newton's law for the inclined plane itself. Okay, and after that this is pure math. You carry through the reduction, and this is what you end up with. Okay, so the choice of the reference frame is critical to solving the problem. Okay, uh, there are other ways to solve this, but this is a relatively easy method to do. Okay? So I hope we get some motivation by solving a relatively complex problem of this nature, and it will help us to conceptualize solutions to more complex problems